Hello there, I'm Liz McDaniel, and this presentation is about action potential of cardiac contractile cells, also known as cardiomyocytes. This is for Human Physiology 2 with Dr. Waller at Grand Canyon University. In this presentation, I will briefly introduce cardiac cells and how they differ from other muscle types before going a little bit deeper into the molecular mechanism of that action potential. I will talk about what makes the cardiac contractile action potential so unique, and I'm going to discuss how the excitation-contraction coupling of cardiac contractile cells responds to this action potential, and how contraction is maintained throughout the heart so that these muscle cells contract in unison. And finally, I'm going to discuss some of the problems that can occur when there are issues with this contractile action potential or the muscle fibers involved, and with contraction, and what treatments, if any, are available for those. Just to briefly provide some background, the heart consists of two primary tissue types. We have the electrical system of the heart, which provides the initial neural pacemaker activity, and this consists of the sinoatrial node, which is here, and the atrioventricular nodes, right there. Which extend through these little bundles called the bundles of His, which are right here, and into these special fibers called the Purkinje fibers around the left and right ventricles. This whole electrical system makes up just 1% of heart tissue. The other 99% is contractile muscle tissue. And that is what I'm going to focus on today. You likely already know that the heart is a dual pumping mechanism and works as a single finely tuned machine, or at least ideally it works that way, in order to enable individual heart fibers to contract simultaneously. There are special gap junctions which transmit the action potential from cell to cell. And just to reiterate, the heartbeat is maintained by that 1% of those autorhythmic tissue, as well as something called the CA2 plus clock mechanism. But this presentation is about what happens after that initiation of action potential, which is the action potential of that contractile muscle tissue, again called the cardiomyocytes, which is the other 99% of tissue, and why it is so unique. And if you look at this comparison of the three muscle types on top, you can see there are some obvious structural differences in these muscle types, and these differences reflect their functions and the way that the action potentials are transmitted across the muscle tissue. Skeletal muscle is connected to our bones, and its contraction is the result of neural impulses from our brain, so it is voluntary. Smooth muscle is not striated. But it is involuntary, meaning we don't control the contraction of smooth muscle consciously. And cardiac muscle, which is obviously the focus of this presentation, is striated, but it's also involuntary. And you can see here on the right that it's also branched. Got these little connections. That is to say that the cardiac muscle fibers are meticulously connected to each other so that their contraction occurs simultaneously. This contraction, as I stated previously, is regulated by the sinoatrial node and the atrioventricular nodes. Cardiac muscle, unlike skeletal muscle, relies on aerobic metabolism. It has a large number of mitochondria to support this. And once again, those intercalated discs and gap junctions enable cardiac muscle fibers to propagate action potentials from the SA and AV nodes simultaneously so that the heart contracts in unison. So this nifty little image shows the different phases of this action potential in a cardiomyocyte. You see on the left here, there is at first this rapid depolarization due to the influx of calcium and sodium ions. And then once peak is reached, right about here, there's a brief repolarization where it drops down just a little bit and then tapers off. This is phase 2 and is referred to as a plateau. And this is caused by a second influx of calcium ions, which are brought in by the activation of certain channels called L-type that's long-lasting. They're very slow calcium channels, in addition to a decrease in potassium permeability due to briefly opened transient potassium channels and leaky potassium channels. And finally, we have this rapid repolarization phase, which is caused by the inactivation of calcium channels as well as delayed activation of ordinary voltage-gated potassium channels. The sudden increase in potassium permeability causes positively charged potassium ions to leave toward their concentration gradient, causing the membrane potential to return to resting, where leaky potassium channels open once again so that this process can repeat. And just a quick note on this one, while I do cite all of my visual sources on a source page, I thought this little GIF was too cool not to mention. This is from Michael Coleman at physicsoftheheart.com, and I have included the URL on this page as well if you want to see his work. This little cartoon is really helpful to visualize how these channels affect the voltage across the membrane. So this far left yellow channel right here is that primary voltage gated sodium channel, and this is responsible for the rapid depolarization up from resting potential. There, I got it. To about 30 millivolts. This one has it like at almost 50. The next phase is the slight repolarization down due to potassium efflux. That's this one right here. Through transient potassium channels. Next, we have slow L-type calcium channels in combination with the decreased potassium permeability, allowing for this plateau right here. So that's this one and this one. And finally, rapid repolarization caused by inactivation of these calcium channels and the delayed activation of voltage-gated potassium channels, allowing a slow return to resting potential as the potassium exits toward its concentration gradient. This process is maintained by the reopening of leaky potassium channels before beginning again. And I thought these images were really helpful to show how that action potential translates to cardiac muscle contraction. So similar to skeletal muscle, and action potential in cardiac cells from the SA node travels down T tubules, allowing a small amount of calcium right here from extracellular fluid to increase membrane potential just slightly. And then a second, much larger release called a Ca2 spark is then induced by this initial calcium release through special channels called ryanodine CO2 plus channels, Ca2 plus channels. This large increase in cytosolic calcium then triggers the troponin-tropomyosin complex to be released from the myosin binding sites in cardiac sarcomeres, allowing cross bridges to form and enabling muscle contraction. If you look at this image on the right, you can see how that action potential, which is here, is juxtaposed along the muscle contraction. The plateau and the action potential enables a longer cardiac muscle contraction, about 100 times longer than that in skeletal muscle, so that blood can be fully squeezed into circulation with each contraction. And in addition to having a longer contraction period and plateau, cardiac muscle has a longer refractory period. So this allows the heart to fully refill between contractions, and it also ensures that the heart will not enter a state of tetany or prolonged contraction, which would be deadly. In fact, heart muscle is incapable of being excited until the membrane fully recovers, and then those starting sodium channels can be activated once again. And I promised some abnormalities, so here we go. Some of them include discrepancies in rate, rhythm, or the quality of heart muscle. Heart rate abnormalities include tachycardia, which is a rapid heart rate, or bradycardia, which is abnormally slow. Interventions for tachycardic episodes can range from simple, such as vagal maneuvers like bearing down, coughing, or putting ice on one's face, or more complex, such as medication or surgically installing a pacemaker or even a defibrillator. For bradycardia, treatments also range from medications such as atropine to surgical intervention. Other abnormalities occur related to heart rhythm. An atrial flutter occurs when rapid sequences of atrial depolarizations between 200 and 380 beats per minute Atrial fibrillation causes atrial contractions, which are not synchronized, and they're very chaotic because the impulses reach the AV nodes so irregularly that ventricular rhythm is also erratic. This causes contractions that are too weak. Ventricular fibrillation occurs when multiple impulses travel in all directions around ventricles and results in disorganized and chaotic contractions. This is very serious and can result in brain damage or even death if not improved with compression or defibrillation. Myocardial ischemia occurs when not enough oxygen is delivered to heart tissue. One type of this is acute myocardial infarction, which is also known as a heart attack, and it can be detected by a blood test that measures special heart repair enzymes. And this is where I got all of my pictures from. And here are my references. Thank you.